So we're going to finish up with our calculations, but first of all, what story is this from? Aiden.
I don't know what story it's from, but what's with the 3, 2, 1 go thing?
It's recording.
Oh.
I'm recording the lectures. I'm recording lectures so I can put it online. Yes?
From the Odyssey.
From the Odyssey. How'd you know that?
Because I saw the tab before.
Yeah, I see the tab up there now. Okay, so this is this guy's named Polyphemus. I don't think he's actually called Polyphemus in the Odyssey itself, but I guess tradition says his name is Polyphemus. The reason I put him up there is because tradition has it that he used to, I think it was after he was blinded, he used to keep track of his sheep by sitting at the door of his cave, and whenever one went through, he would move a rock from one pile to another. And that's a primitive form of counting, or of measurement. Primitive form of measurement. It's measuring the size of a sheep herd by doing what? By comparing it to something else, the size of a pile of rocks, right? Now, it turns out that every measurement is only this. Same thing, comparing one thing to another. What is a milliliter? A milliliter is a cubic centimeter. What's a cubic centimeter? It's a cubed length. What is a centimeter? A hundredth of a meter. What is a meter? It's some fraction of the distance that light can travel in a certain amount of time. There you go. So we are literally comparing the amount of water in this to a small fraction of the distance that light can travel in a certain amount of time. When we weigh something in grams, we are actually comparing it to a chunk of platinum-coated metal in France. Or maybe it's pure platinum, I'm not sure. It's under glass in some vault in France. That's all we're doing. So we got a little more sophisticated than Polyphemus. We're doing the same thing, but the reason I bring it up is because if we think of another illustration here, it brings even a more important aspect of measurement to light. You see his jug here. Let's say that Polyphemus was going to use this jug to measure the amount of milk produced by his sheep herd to see. Maybe he's going to do an experiment even, and he's going to see how different grazing practices affect his milk production. Right? So he's going to have a control group, and he's going to have his sheep, and he wants to measure the milk. Right? So as he's producing the milk, he fills up a jug. He says, 1 jug. Okay? Or he moves a rock. He fills up another jug. All right, and that's fine, and we don't really have any problems as long as his jug is filled right up to the top every time. But what happens when he gets to the end and it doesn't fill up all the way? Now he's got to do something that I said we always have to do in measurement, and that's called estimation. He's got to say, that's a half a jug. Is it? Or is it a little less than a half? Or is it a little more than a half? Right? Or is it a quarter? Or is it a little less than a quarter? A little more than a quarter? So he's estimating. And there's uncertainty. No matter how small he makes that darn jug, he's got the same problem. Now, the problem becomes less, right? He becomes more and more precise the smaller he makes his jug. And maybe he's got a whole set of jugs. He's got a jug, a half a jug, a quarter of a jug, a 16th of a jug, and so on, right? Maybe he's got tiny little thimble jugs that are 1/128th or something like that. 1/256th of a jug. But what if that thing's only half filled at the end? Right? Now, the problem is even worse than that, because I'm talking as if he could know that a jug was perfectly filled. But is that true? What if it's a little bit below the edge? What if it's kind of up a little bit? Even the process of saying this jug is full includes some uncertainty. So my point is that this whole uncertainty thing is inherent in measurement. It is not a flaw in human nature, or in our eyes, or in our brains. It's actually a very powerful feature of our brains, that we can exercise this sort of judgment and estimation. And if you were a robot, it probably be even worse for you, because you would probably have a harder time taking other things into account, things that we intuitively use when we're making that judgment. You follow me? So being a robot would not solve the problem. Using an instrument would not necessarily solve the problem. Now, you can narrow it down. You can make it less. I can switch instruments and make it more precise. So instead of using this, I can use this, and I have less of a problem. Polyphemus could have a whole set of jugs at different fractions of sizes, and he could help himself get more precise data. Right? Okay. Questions? Okay. Sorry about that. All right, I want to talk about calculating with uncertainty. And let's just throw out a couple numbers here so that we can see. Let's say these are masses of a sample. And I'm going to do this mass 3 times. So I'm measuring the mass 3 times. Four times. Let's do it 5 times. So I've got all these masses, and I want to express my mass with my plus or minus values, so I can use my maximum deviation or my average deviation. Let's use the average deviation method. So first of all, my mean for this data, 1.234. .2346. All right. Now, if I subtract this from each of these values, I'll get my deviations. Now I'm just going to get the absolute values here. Sorry, I messed this up. This is 6, and this one is 2.4. Take the average of these. For the average deviation. So if I wanted to use the maximum deviation, I would take the largest one, and my uncertainty would be 0.002. If I want to use the average deviation, then I'm going to add all these up and divide them by 5. And I get 0.00112, and I'm going to shave that off so that it's only got one non-zero digit, and then I'm going to make sure that my decimal places match in my measurement, and that's my final answer in grams. This then is called the average deviation. And it's a little bit closer to the standard deviation. So we talked about maximum deviation, where we just picked the largest. So maximum deviation here would be 0.0024. If we want something a little bit more realistic, we'll use the average deviation, because this is going to be, using this right here, 1.235 plus or minus 0.001, what this does is it says it's more likely that the true value is in this range. It kind of excludes the data points that are more outliers. Okay? So it's a little more realistic. The standard deviation is much more similar to this than to the maximum deviation method. It's just a different kind of an average. Questions about that process? I'm actually going to leave it up to you on labs whether you use the maximum deviation or the average. I expect you might choose to use the maximum oftentimes, although, as we'll see, there are times when you won't want to use the maximum deviation when your data are maybe a little sloppier, and it may decrease your chances of drawing a conclusion, a reasonable conclusion, I should say. Any other questions about these? So I wanted to review the average deviation, and I've got a practice sheet for you to do, hopefully second half of class or so. But first, let's talk about calculating with uncertainty. So how do we perform calculations when we already have plus or minus values on the numbers? How do we carry those plus or minus values through the calculation? Did I start talking about this last time? Let's start very simple, addition and subtraction. Now, you've all heard of something called accumulated error problem. If you assume that you've got this uncertainty every time you take a measurement, then if you're adding measurements together, you can make it worse. Right? So if I'm taking this ruler and I'm trying to measure the room width, by the time I get to the end, I'm probably going to be off by a fair amount. Right? Even though the first measurement might be pretty good. That's accumulated error. So basically, all we do is add the uncertainties. When I do wetland delineations, so I'm a soil scientist and I can flag wetlands for people that want to build a house or whatever. Of course, nobody's building houses anymore in the last couple of years, but if it ever comes back, then I'll probably do it again. But when I'm out there, I've got a map of the property, I've got a compass, and I have to find my way around. So what I do is I pace off the property lines to try to find the property corner, for example, out in the woods. And I know my pace is 5 feet, more or less. Now that's okay if I'm just measuring 100 feet, or even 200, I'm pretty good. But when the property lines say 1,000 feet, or 1,500 feet, then by the time I get out there, I'm way off. It's almost useless. I'll get out there and I'm not sure if I'm 1,000 feet or 800 or 1,200, and I've got a 200 or 300 foot radius that I think the corner might be in, right? So I've got issues. But my point is, the further out I get, the more error I accumulate. You know, I had to step over a log here, so it changed my pace. Had to run from a wild animal here, and it changed my thing. Jump over a crevasse, right? Whatever it is, or even if it's not that extreme, it's just my pace does vary a little bit, and for one thing, it's not exactly 5, even on flat ground. So I accumulate error. This is very simple, though, when we're dealing with measurements. We just add the errors. Now, let's look at a practical example. Let's say I'm weighing something on a piece of weighing paper, and then I have to subtract the weighing paper out. So we'll say something like this: the sample plus the weighing paper. And this is a very common thing that we'll be doing is subtracting weighing paper or some kind of weighing vessel, maybe a crucible, out of the total mass. Let's say the total mass with the weighing paper is 4.546 grams, and the weighing paper alone is 0.494 grams. All right. Now, I forgot to put the uncertainty in here. Both of these will have uncertainty, and they might be multiple measurements. Maybe I just estimated. I look at the balance and I say, oh, I think I'm within 0.002 on both of these. All right? These are grams. I subtract these two numbers. .052 plus or minus 0.004. Now notice, even though I'm subtracting the numbers, I add their uncertainties. The same is true in addition. Just simply add the uncertainties. Very simple. Now, it's actually overly simple because why is that really not realistic to do that? Anybody want to take a guess? Why would I say that? If you take AP Stats, you're not going to just add uncertainties. You're going to do a more complicated calculation. Okay, yeah. So you're right. This is worst case scenario. This is as bad as it could get. Not only do they both have to be the maximum error possible, but they have to be in the same direction. Follow me? And that's a big factor. The direction of the error is actually not likely to be extreme and in the same direction in both your measurements or in all of your measurements. If all we ever do is add the errors, then that's basically what we're getting. Worst case scenario. Every time I do a pace, I'm probably not off in the same direction every time. Sometimes my pace is a little short, sometimes it's a little long, and there's a canceling out effect there that actually makes the situation a little bit better. So it'd probably be a lot more realistic if this were closer to .002. But I do have to take into account accumulated error, so it's going to be between 2 and 4 somewhere. But it's much simpler for us to just add them together, so that's what we do, and that's what you'll do in physics as well, I believe. Just add them together. Somebody had a hand up? No? So that's pretty simple, right? Unfortunately, multiplication and division is a little tougher. And let's start with an explanation of why. And it turns out when you're multiplying and dividing numbers, you can't just add the uncertainties. The simplest reason is because you could be multiplying or dividing numbers with different units. Grams per cubic centimeter. So you're dividing grams by cubic centimeters. You can't add an uncertainty in grams to an uncertainty in cubic centimeters. It doesn't make sense. They're different units. You can divide them because then you're just giving me a ratio. You're not saying they're the same units. But let's look at a little more detail at, even if we have the same units, we can't just add them. Let's say I'm measuring an object that's something like this. And I want to know the area. So I want to get the area of this thing, and I find out it is 10.0 meters plus or minus 0.1. 10.0 plus or minus 0.1 meters. So I'm able to measure within the nearest decimeter. Now on this side, it's 1 plus or minus 0.1. Now what's my area? My area is 10 square meters, right? And I might be tempted to just add those and do this. Okay? But I can't do that. Now, first of all, what would this be saying? This would be saying it could range like this, 9.8 to 10.2. But is that true? Look at your uncertainty. Let's use these ranges. So in other words, this tells me I could be as high as 1.1 or as low as 0.9. And this one tells me I range from 10.1 to 9.9, right? So let's do all the calculations here. I could be as low as 0.9 times 9.9, as high as 1.1 times 10. See what I'm doing here? I'm picking my lowest possible width and multiplying by the lowest possible length, picking my highest possible width, multiplying by the highest possible length. So I get 9.9 times 0.9 I'm just looking at what the range would be if I just did the calculations with the lowest and highest possible lengths and widths. See that? So I can't use 0.2 because it underestimates the uncertainty in my answer. See, if I've got 0.1 meters uncertainty in my length, that means my length could be anywhere from 9.9 to 10.1. My width, likewise, could be anywhere from 0.9 to 1.1. That means my area could be anywhere from 8.91 to 11. Okay? That's my true uncertainty. Whereas if I just added 0.1 to 0.1 like I did with the addition and subtraction, I'd get 0.2, and that would give me a false sense of precision. So how do we get around this? We still add the uncertainties, but we add them as percentages. See, because here's what's going on. What's going on is that this, notice, maybe I'm using the same ruler to do the length and width. And so my uncertainty is 0.1 both times. See that? But in this case, 0.1 is 10% of my measurement. In this case, it's 1%. Follow me? So I have 10% error here, 1% error here, 11% potential error in my answer. Follow me? And this is not 11%. That's 2%. So it's about percentages, and that's the answer. That's how we do it. When we're doing multiplication or division with uncertainties, you still add them. We're still accumulating error, but you add them as percentages. Figure out what percentage they are first, what percentage your uncertainty is, and then add those and apply it to your answer. So let's see how I would do that in this case. So we have to add uncertainties. Have to add uncertainties as percentages. It's a multi-step process here, but I'll show you how it works in this case. Basically, I take 0.1, so I'm going to use the length measurement first. 0.1 meters over 10 meters is, and times 100. You don't actually have to go all the way to percent. You can leave it as a decimal fraction, but I'll go all the way to percentage here just to illustrate. This is 1%. And then I've got 0.1 meters over 1 meter on the width of this thing times 100. That's 10%. Okay? 10% plus 1% is 11% total. That's the uncertainty in my answer. Okay. Questions about what I just did? Yes?
So do we write it as plus or minus 11%? Or do
Okay,
you want the decimal?
That's where we're going. So we're going to want to convert it back into the proper units now. Right now it's a percentage. It's a unitless percentage. So here's what I'm going to do. I'm going to write the answer, which is 1 times 10, or 10 square meters, plus or minus. Now, you could write 10 plus or minus 11%, all right? And there's nothing wrong with that. But we'd prefer to convert the 11% into meters, square meters. So basically what I'm going to do here is I'm going to take 11% of 10, which is what? 1.1? So I write 1.1, right? And that's square meters. And then I correct it because I don't want to have two non-zero digits here. So I'm going to write 10 plus or minus 1 square meters. That was a little fast. Questions?
Wait, what'd you do at the end?
So I had 11%.
Yeah.
Okay, that was my accumulated error, 11%. What I did is I could just write 10 plus or minus 11%. But that's not preferable.
I got the 10%, I mean, the 10.0, plus or minus 1.1. Why isn't it plus or minus 1?
Ah, okay. Why didn't I just leave it like this?
Yeah,
why did I write
why did you take off the 0.0 and then the 1.1?
Okay, good question. I did that because this plus or minus 1.1 tells me I'm not sure about the ones place. It tells me there's uncertainty in the ones place, okay? I'm sure about the tens place here, that it's over 10. Actually, I'm not sure it's over 10, could be 9. But I'm not sure about the ones place. And I actually know nothing about the tens. So I'm not, by showing you 10.0, I'm implying that I know something about that first decimal place when I really know nothing about it. It could be, this number right here could be anything from 0 through 9, that digit. Think about it. If my range is from 9 to 11, then this number could be anything from 0 through 9.
Right, but I get that. Why does that make you have to take off the 0.1 at the end of the 0.1?
Well, first of all, not everybody would do that, would shave that off. I think Dr. Bent lets you keep 2 digits in the uncertainty, 2 non-zero digits. I prefer to do that for the same reason, for the same argument here. I don't think it adds to the information on this side. Okay? If I'm uncertain in the ones, then I don't really need to know about the uncertainty in the tens.
Right. Very good.
So in general, those are the rules we'll apply. There's 2 rules. We want 1 non-zero digit in the uncertainty, and then we want the decimal places to agree. With our answer. Okay? So first, adjust your uncertainty so that you only have 1 non-zero digit, and then in your actual measurement, make sure the number, shave off the decimal places to match the uncertainty. Okay? And that'll work for you. Questions on that? This is called the propagation of error. And like I said, if you take AP Stats, you will get much more sophisticated with this sort of thing. Yes?
Do you have to know by name propagation of error?
No. This is oversimplified, but so be it. It's important to know about your uncertainty. It's going to allow us to draw conclusions. If you were an engineer, you would definitely want to know your uncertainty. When you're estimating the load on a bridge, you want to know what your uncertainty is in that estimation, right? You always want to know about it. Nothing's exact, you know? When they make parts for planes, there's always what they call a tolerance, which is the precision with which they make the part in terms of the sizes of everything, right? Nothing's exact, so nothing's perfect. It's all a matter of what your tolerance is, right? Any questions before we do some practice? I didn't do this yet, right? So we're going to do some practice. I want you to do the front first, although if you finish, you can start working on the back. The back has the calculations. The front is just some practice with writing the plus or minus notation. We talked about accuracy and precision last time. Is that right? Yeah. And the dartboards or whatever, targets. I realized I was supposed to